Hey there, and welcome. Today we're diving deep, right into the heart of matter itself. Yup, we're talking about nuclear physics. We're going to explore the universe's most powerful, most compact energy source, the absolutely incredible atomic nucleus.
All right, to get us started, let me ask you something. What single force powers the sun, generates the electricity lighting up your room right now, and even lets doctors see inside the human body? Well, the answer to all of that is the power locked away inside the atomic core, and we're about to unpack exactly how that works.
So let's start by zooming in. And I mean way, way in. We're going to skip right past the electrons that all the chemists talk about and go straight to the center of it all, to the atom's hidden powerhouse. Okay, now get this, because the scale here is just mind-boggling. Picture a giant football stadium. If the whole atom were the size of that stadium, the nucleus would be like a single marble sitting right on the 50-yard line. A tiny marble. And yet, that little thing contains nearly all the mass and a truly staggering amount of energy. It's incredible.
So, what's actually packed inside this unbelievably dense little core? Well, let's meet the key players and discover the ultimate cosmic superglue that holds it all together against truly impossible odds. So inside, it's actually pretty simple. You've really only got two types of particles running the show. You've got your protons, which have a positive charge, and you've got your neutrons, which, just like the name says, are neutral, no charge at all. Seems simple, right? But, that simple setup leads to a huge, huge question.
And this is the big puzzle. You've played with magnets, right? You know how you try to push the two positive ends together and they just refuse. They push each other away. Well, the same thing is true for electrical charges. So how in the world do you cram all of these positively charged protons into a space that small without the whole thing just instantly blowing itself apart?
Well, the answer is something truly epic: the strong nuclear force. This is one of the fundamental forces of the entire universe, and it is unbelievably powerful. It's more than 100 times stronger than the electrical force, trying to tear the nucleus apart. But here's the catch. It only works over incredibly short distances. Think of it like the universe's strongest superglue, but it only gets sticky when things are really close together, binding those protons and neutrons tight.
But, that balance of forces isn't always perfect. Sometimes that cosmic glue isn't quite right for the mix of particles. Some atomic nuclei are just naturally unstable. So let's take a look at what happens when the core of an atom has an unstable heart. Okay, so here's the deal. Nuclei basically come in two flavors. You have the stable ones, which are perfectly happy to stay just as they are forever. And then you have the unstable ones. An unstable nucleus is what we call radioactive, and it's basically living on borrowed time. It can't stay in its current state. It's going to change to try and find a more stable arrangement. And that change happens through what's called radioactive decay. It happens in a few main ways. First, you've got alpha decay, where the nucleus literally just spits out a chunk of itself, two protons and two neutrons. Then there's beta decay, which is really wild. A neutron inside the nucleus actually transforms into a proton. And finally, there's gamma decay, where the nucleus doesn't lose any particles, it just calms down by releasing a burst of pure high-frequency energy. Now here's what's so cool. While you can never, ever predict when one single atom is going to decay, if you have a big group of them, the whole process is incredibly predictable. We measure this with something called a half-life. That's just the time it takes for half of your sample to decay. So after one half-life, you've got 50% left. After a second one, you're down to 25%, and so on. It's this perfect, predictable clock that lets us do amazing things, like carbon dating ancient artifacts. All right, so we know there's a ton of energy holding that nucleus together, and we know unstable nuclei can release some of it on their own. But what happens when we humans decide to intentionally unlock that power? That's where things get really interesting. And really, there are two main ways we figured out how to do this. First up, you have fission. This is all about taking a big, heavy nucleus, think uranium, and splitting it apart into smaller pieces. This is the process that powers all of our nuclear power plants. On the flip side, you have fusion. This is the exact opposite. You take two really light nuclei and you smash them together to make a heavier one. This is what's happening in the core of the sun right now. But wait a minute. Why? Why does splitting or combining atoms release so much energy? The answer comes from probably the most famous equation on the entire planet, thanks to Albert Einstein.
You see, what Einstein's famous equation really tells us is that mass and energy, they're basically the same thing. They're two sides of the same coin. In both fission and fusion, a tiny, tiny amount of physical mass actually disappears, but it's not gone. It's converted directly into a massive amount of energy. And here's the kicker, that c² part, that's the speed of light, squared. It is a huge number. So you convert even a speck of mass and you get a tremendous, almost unbelievable amount of energy in return.
Okay, wow. We have gone from the impossibly small to the incredibly powerful. So let's zoom all the way back out now and see how this fundamental physics shapes our world in ways you might not even realize.
And believe me, this stuff isn't just about power plants. The very same principles we've been talking about are absolutely critical for modern medicine. From PET scans that let doctors see how your body is functioning, to radiation therapy that precisely targets cancer cells. This physics powers the space probes exploring the outer solar system, and it's what lets archaeologists figure out exactly how old an ancient fossil is. It's all around us.
So we end up here. This tiny, tiny atomic core holds an almost unimaginable amount of power. It's given us the light of the stars, new ways to generate electricity, and tools to heal and to explore our past. The science is incredible. The power is undeniable. The only real question left is, what do we as a species choose to do with it next?